Hello everyone, welcome to this lecture. So, in this lecture we will see the analysis of the GRR degree reduction method. We will see the complexity analysis as well as the security analysis. Okay. So, this is the summary of the GRR degree reduction method, starting with secret sharing of A and B, which are secret shared through degree T. We compute a secret sharing of A B also with degree T, and the resultant shares lie on a random polynomial of degree T. And basically the idea behind the GRR degree reduction method is to securely compute this linear function. So, you can see the beauty of the method. To do a degree reduction, we actually use the fact that we have to compute a linear function of private inputs available with the respective parties, and linear functions can be very easily computed if the parties just secret share their respective inputs. Okay. So, what will be the complexity here, namely how many rounds will be required to do the degree reduction and how much communication is needed. So, if you see here, each party Pi has to secret share its private input Ki for this function that we have, that I have circled here. Okay. So, for instance, party 1 has to secret share K1, party P2 has to secret share K2, party I has to secret share Ki, and party N has to secret share Kn, right. So, P1 will be secret sharing K1 by picking a random polynomial of degree T and distributing shares. Similarly, P2 will be doing, Pi will be doing, and Pn will be doing, and then finally we take the linear combination. So, now even though in the slide I have shown that K1 is picked and then K2 is picked and then Ki is secret shared and then Kn is secret shared, that need not be the case when we are actually implementing it, because Pi, when P1 is secret sharing the value K1 through this K1 polynomial, independently and in parallel Pi, P2, any other party can independently pick its secret sharing polynomial and start distributing the shares of the corresponding Ki values. Okay. So, that means in terms of interaction, this requires only one round of communication. That means if P1 starts secret sharing its input K1, at the same time P2 can start secret sharing its input Pi can start secret sharing its input Ki, P2 can start secret sharing its input K2, and Pn can start secret sharing its input Kn. So, that is why in terms of number of rounds, this required only one communication round, and there are n instances of secret sharing here involved, because there are n inputs of this function, each of which has to be secret shared. So, there are n instances of secret sharing involved. We know that for one instance of secret sharing, order n field elements have to be communicated, because n number of shares have to be communicated or distributed. So, for n instances of Samir secret sharing, total n square field elements have to be communicated. That means, to apply the GRR degree reduction method, once we have to, the parties have to interact for one round and n square field elements have to be communicated. Now, what about the security analysis, right. So, remember, in the degree reduction problem, the goal was that no additional information about A and B should be revealed. The parties should start with their components of the A vector, B vector, and finally should obtain their component of the C vector. In the process, no additional information about A or B or C should be revealed. But you can see in the process, the GRR degree reduction method, there are several instances of secret sharing which are involved. During the secret sharing instances, the parties or the adversary will be receiving shares of the K1 value, the shares of the K2 value, the shares of the Kn value. The question is, will learning those shares reveal anything additional about the A or B, right. So, as I said, if I consider the party Pi to be honest, imagine Pi is the honest party. So, earlier as part of the input, ai and bi are held only by the party pi, and hence ki is held only by the party pi. For the A polynomial, T shares were available with the adversary, for the B polynomial, T shares were available with the adversary. And for this ki value, adversary will now obtain T shares, assuming that say the first T parties are the bad parties and under the control of the adversary. But will learning those T shares help the adversary to learn or conclude anything about ki? And the answer is no, because this ki is shared by an instance of Samir secret sharing, and as part of the instance of Samir secret sharing, the ith party will the adversary will obtain T shares, and those T shares are randomly distributed. They could be the shares of any candidate ki from the field. Adversary cannot pinpoint what exactly is the value of ki which has been secret shared. In the same way, if I consider the nth party to be an honest party corresponding to kn, the adversary will obtain T random shares, and the property of Samir secret sharing is that you take any T shares available with the adversary generated as part of the Samir secret sharing, they are randomly distributed. They could be the shares for kn being 0, they could be the shares for kn being 1 for any candidate kn from the field. That means, even though information about k1, k2, ki, kn are made available in the form of their shares, adversary will have only T shares for each of the ki values which are under the control of the honest parties, and hence those ki values remain unknown from the viewpoint of the adversary. That means, adversary does not learn or infer any additional information when they receive the shares of those ki values, and hence we can easily say that they can be easily recreated or simulated by a simulator. So, remember, when we formally defined the privacy property for a generic MPC protocol, the idea behind the security definition was to capture the fact that whatever information bad parties receive from the honest parties as part of its view, they can be recreated without even talking to the honest parties. That means, if we give the simulator that okay, this is the input and the output of the corrupt guys, based on this can you recreate whatever values, whatever messages the honest parties would have communicated in the real execution of the MPC protocol, the simulator should be able to do that. Only then we can say that the interaction from the honest parties for the corrupt guys is of no use, right. So, now what we are seeing here is, what we are arguing here is that even in the GRR degree reduction method, whatever were the shares of A and B that are under the control of adversary, they will be known, but whatever information regarding the ki values that adversary is receiving as part of sharing of those ki values by the ith party, those values are randomly distributed, and hence they can be easily simulated, they can be easily recreated even without actually talking with the ith party. That means, without talking with the ith party, I mean in the sense that adversary will already know that the T shares that I am going to receive, that they are just random field elements from the field. So, I can myself write down what are those values. In the sense, I can easily write down the probability distribution of those T values that I will be receiving. That means, interacting with honest PIs in this GRR degree reduction method is of no advantage for the adversary. So, that shows that the degree reduction method, the GRR degree reduction method indeed satisfies the privacy requirement as well. That means, without even revealing any additional information about the A values, B values, we can convert it into, we can convert the shares of the A value and the shares of the B value into the shares of the C value lying on a random T degree polynomial. Thank you.